Hey class, this is 7.6, 7.7 notes. So I'm going to run through a bunch of stuff. I'm actually going to extend, the notes are going to go a little bit past 7.7, so you won't be quizzed on what comes after 7.7, and I'll make sure you know this in the screencast. But I do want to just finish it out. We'll talk about some of the non-metal groups for 7.8. So let's take a look. The first part of this is about properties of metals, nonmetals, and metalloids. So if you take a look at the periodic table, any periodic table, you will see that most 75% or more, here we go, there we go, will be metals. So we're talking about all of these are considered to be metals. And as you can see in my periodic table here, more metallic character increases as you go down, and it increases as you go from right to left. Which means that francium, if you want to remember a trend for metallic character, just remember francium is the most metallic metal. And where it is on the periodic table will tell you how the trend goes. So it goes, it increases as you go down and increases as you go to the left. Just like as a side note, the same exact thing is true for fluorine. So if I'm talking about nonmetals now, then the most reactive non-metal then tends to increase as you go towards fluorine, which means going up a group. Notice it's the opposite as metals, going up a group and going to the right. Notice that I did not say anything about this group here. These are the most stable. I'm sure you know that by now because of the electron configurations. Those electron configurations are, for lack of a better term, perfect and do not want to gain electrons or lose electrons, whereas right next door in the halogens, the 7A, fluorine, chlorine, bromine, iodine, acetine, they all want to gain one electron to look like the noble gases, which is why on the other side that lithium, sodium, potassium, and rubidium and cesium are all very, very reactive because they want to lose one electron to look like a noble gas. So sodium, number 11, loses one electron to have 10 electrons. And what else has 10 electrons? Well, of course, neon has 10 electrons, and neon's electron configuration is the second most stable electron configuration on the periodic table, helium being obviously number 1. So helium is the most inactive element on the periodic table. And I'll talk more about that later on. So let's keep going. That's just a brief overview of what's going on. So take a look at some metals. Metals have shiny luster. Luster means shiny, so like shiny, shiny is what that means. Various colors, although most are silvery, like gray, silver, and there are some that obviously like the copper or gold color, but for the most part they are silver. Solids during room temperature, but they also tend to be malleable and ductile, some less so than others. Some, like lead, were used early in existence of humans because it was so ductile, so malleable. You could form it in many different shapes. Even like they made pipes. Romans made pipes out of lead. They say one of the reasons for the downfall of the Roman Empire because they all got lead poisoning from the pipes that they made out of lead. They are good conductors of heat and electricity. For electricity, gold is one of the best conductors, platinum one of the best conductors. Unfortunately, because of their inert nature, they are also known as they're very popular for jewelry, which makes them very expensive. Did you know that in my chemistry room here, you could fit all of the known platinum ever mined into my chemistry room? That's how little of it they've actually mined. I'm not sure how much is on Earth, but it's not nearly as much as you think it would be. Most metal oxides and ionic solids are basic. That means that when you mix a metal like sodium and oxygen together, there's a fantastic reaction because that oxygen comes from water. That's a very well-known one we'll get into. But the sodium oxide would be then basic, tend to be basic. So metal oxides are basic. They tend to form cations in aqueous solutions. Okay, what about nonmetals? do not have luster or various colors. They do have various colors. Sulfur is yellow, iodine is like a dark purple, bromine is like a brown, which is kind of strange. Maybe like a purplish brown, that's kind of weird. Solids are usually brittle. Some are hard, some are soft. Some of the solids, like, of course, carbon. One of the allotropes of carbon is, of course, diamond, the hardest material that we have. Poor conductors of heat and electricity. Many are used as insulators. Most nonmetals are molecular substances. That means that when you put a nonmetal and a nonmetal together, that they are bonding, they are sharing electrons, they are not transferring electrons like ionic substances would do, and they form acidic solutions. So tend to form anions and oxyanions. Oxyanions is a fancy word for saying polyatomic ions. So that would be stuff like NO3 with a -1, and so on, SO4, and so on, okay, in aqueous solutions. So the difference between metals and nonmetals, actually, they tend to be opposites of each other. So if a metal is shiny, a nonmetal is not. If a metal is malleable or able to be shaped or pounded into a shape, then the solids of nonmetals tends not to be. If most metals are solids, then a lot of nonmetals are actually gases, and one of them is a liquid. Good conductors of heat most nonmetals are insulators. Most metals are basic, and most nonmetals are acidic. Okay, so opposites of each other. Let me just keep going here. So here we go. Take a look just quickly. Metals tend to form cations. Take a look at this chart. What it has listed here are the most common metals that we see as compounds. And when they form cations, that means a plus charge is because they get rid of electrons. You can see that from here over, most of the charges are +1 and +2. It's only when we get to the post-transition metals in here where we have charges that tend to be more than that. Now, some of them, like iron, can go up to a +6, but that's not the normal thing. Okay, so take a look on the right-hand side. Obviously, hydrogen can lose 1 electron to be a +1, or it can gain 1 electron to be a -1 that we see here. And if it gains a -1, if it gains an electron to be a -1, then it's very similar to the halogens. So notice that the pattern goes -3, -2, -1 as we get closer to the noble gases. Okay, that's all. Let's keep moving. So metals tend to be lustrous, malleable, ductile, and good conductors of heat and electricity. Repeating myself. Okay, metals form, compounds with metals and nonmetals tend to be ionic. That means electrons transferred, and metal oxides tend to be basic. I've already talked about this stuff. Nonmetals, dull, brittle substances, poor conductors of heat and electricity, tend to gain electrons. Some can give up electrons, but that's not their normal state. Substances containing only nonmetals are molecular compounds. That's true. Even if we have an acid like HCl that gives ions in solution, it's still a molecular compound. So that's kind of not what we tend to think, because there are other compounds that give ions in solution, and those tend to be ionic compounds. So this is one molecular that gives ions in solutions, which is not the normal. I just wanted to point that out. Most nonmetal oxides are acidic. Again, we said that before. So metalloids, they have characteristics of both. Some of the nonmetals, such as silicon, it can be, under certain circumstances, an insulator, and it can also be a conductor, which is why it's used for circuit boards. So for instance, silicon looks shiny but is brittle and fairly poor conductor. It's fairly poor conductor under certain circumstances and a good one under others. So that's 7.6. Let's take a look at some group trends. So the group trends that we want to first take a look at are the alkali metals. Soft metallic solids, and when I say soft, I mean cut with a knife soft. Okay, so I can take sodium metal and cut it with a knife. That's how soft it is. That's softer even than lead. Lead you can scratch with a knife, but for the most part, I'm not sure you can actually cut it with a knife. So names came from Arabic words from ashes, because that's where a lot of the chemical history came from, is from an Arabic origin. So found only as compounds in nature because they are way too reactive. They have low densities. When sodium reacts with water, it actually floats on top because its density has decreased enough that our water is actually more dense. You can see it here for lithium and sodium. They all have densities less than water. If I threw a piece of rubidium in, it would sink until it produced enough like gas to make it float back again. So they also have low ionization energies. Ionization energy, meaning ripping off the outside electron. Of course they're low because they want to lose that electron to have noble gas configurations. So that's something that should be obvious from our electron configuration discussions. So alkaline metals, their reaction with water are famously exothermic. Maybe at some point next week we'll take a look at a demonstration with that. So alkaline metals, except lithium, react with oxygen to form peroxides. So lithium, although it's very reactive, does not readily form peroxides. I'm not sure why. It may be because of the size of lithium is so small. Potassium, rubidium, and cesium also form superoxides. Okay, so what's a peroxide? A peroxide is when oxygen, there's two of them, and they have a -2 charge like this. That's what a peroxide is. So sometimes you will see something like this where it's potassium peroxide, like that. Now, a superoxide is when you have two oxygens and they both together have a -1 charge, which is how we get potassium with a +1 charge as KO2, a superoxide. So they also produce bright colors when placed in a flame. This one here is lithium. This one here is sodium. I was just gonna, why not just use the symbols, moron? And then potassium is the purple one. So red, yellow, and purple for the first three alkaline metals. So what else do we have here? Earth alkaline have higher densities and melting points than alkaline metals, but still relatively low. These densities are still pretty low. This may be more average for a metal, but metals tend to be higher in density than nonmetals and have lower ionization energies than nonmetals. So again though, so this is just like alkaline earth metals are like alkaline metals light, like a cheap imitation of alkaline metals. So alkaline earth metals are still reactive, but they're not quite as reactive as alkaline metals. They're still low in density, but not quite as low in density as alkaline metals. They still have low ionization energies, but still not as low as alkaline metals. So like I said, alkaline earth metals are like alkaline metals light. Okay, Be does not react with water, but as you go down the group, Mg, Ca, Ba, and Ra, they all react readily with water. Some of them, towards the bottom, will react with cold water, which it does make a difference, whether the temperature of the water is cold or hot. Reactivity tends to increase as you go down the group, which is why the hydroxides of alkaline metals tend to be more soluble at the bottom. Magnesium hydroxide, not quite so much, but calcium, strontium, and barium are all readily soluble with water. Oxygen, sulfur, and selenium are non-metals. So here is where it turns from 7.7 to 7.8. I just want to point out a couple of things. I'm going to go through this pretty quickly. Oxygen, sulfur, and selenium are non-metals. Oxygen is way more the reactive one of the three. Tellurium, is a metalloid, which means it has properties of both metals and non-metals. And polonium is radioactive and is not normally seen. Oxygen has two allotropes. Allotropes are forms of the element. So ozone is the one that you hear a lot about because this protects us from UV rays. This is only a very thin layer in the upper atmosphere. And things like carbon dioxide or methane, CH4, really rip it apart and change it to O2. Now O2 is good, obviously, for us, but we would much rather have some kind of ozone layer to help protect us from skin cancer, obviously. So the three anions that you've seen before are oxygen. This happens probably 95% of the time. So anytime you see oxygen in a compound, just assume it has a -2. There are only certain small percentages of like I should say closer to 4.9% of the time, you may see a peroxide. Peroxides are still mildly common. Superoxides are absolutely not common at all. So you may never see a superoxide when we talk about compounds with oxygen. And oxygen obviously tends to be in a lot of compounds. So oxides are very common. Peroxides, much less so, but superoxides are absolutely rare. So a weaker oxidizing agent of oxygen is sulfur. Sulfur tends to be S8, and when it does that, it has a yellow color, which is why those sulfurs are yellow. Then we take a look at the halogens just very quickly. Remember, we are in like bonus notes right now. Prototypical nonmetals, so they are very classically nonmetals. Their properties tend to be very brittle. If they are solid, they tend not to conduct electricity well at all. Name comes from salt formers, halos. I don't know anything about that, but let's just keep moving through this. Notice that each one of these is missing one electron to get to a noble gas configuration, which is what gives them their properties. So the large negative electron affinities, which means that they will gather electrons from anywhere, therefore tend to oxidize other elements easily, react directly with metals to form metal halides. Chlorine used in water to serve as a disinfectant, which means that if you have a pool, you know what I'm talking about. 90% of all pools work on chlorine, some work on bromine, but most of them are chlorine pools. So the last one is noble gases. They are, of course, very, very inactive. They're called noble gases and also inert. They have positive electroaffinities, which means it takes energy to put an electron on them, and they are monatomic gases, which means there's only one of them. So helium floats around by itself, not like H2, not like hydrogen, which is diatomic. Xe forms three compounds. Notice because in Chapter 9 we will get to talk about XeF2, XeF4, and XeF6. Krypton only produces one stable compound, and Ar was very recently, within the last 20 years, developed a compound that has been more stabilized. It's not this one, they found another one. It's not this one, but they found another one where Ar is actually a little bit more stable than the HARF. So that actually was, in the chemistry world, kind of big news. Absolutely no compounds for neon or helium yet. That's it. Thank you guys for paying attention.